go ahead and get started here. All right. This is a little different, okay? So I'm going to need some focus today because this is a process that you're going to need to know how to do, and if you miss today, you're going to be lost for a while, all right? So just make sure you're paying attention. Make sure you're following along. Stop me and ask questions if you don't get it, all right? Because what we're doing here is, you remember the whole electron moving thing that we did kind of at the end of the ionic bonding chapter? Okay, where we took the electrons and we said, all right, sodium's got 1 valence electron, chlorine's got 7. One of them moves over here, okay? We're kind of going to do the same thing with covalent compounds, except now instead of a transfer from one atom to another, then they're going to share them, okay? So they're going to share pairs of electrons. This is on, yeah, good question. I don't have a note sheet in front of me. See if I can find one quickly. Probably not. Back of the first page.
Yeah.
What's the Roman numeral and letter that we're at right now?
The letter is B, but it's like Roman numeral 3.
Okay. All right, I'll get this out so that I can follow along with you guys. All right, so it's right underneath the periodic table on the back of the first page. Okay? Roman numeral 3, letter B. Electron distribution is depicted with Lewis structures. Okay? And this is how you're going to decide how many atoms will bond covalently, and not just how many, but how many electrons they're going to share in between them. Because it turns out they can share more than just 2 electrons. A lot of times it's only 2, but sometimes they can share more than that. Okay? So this is going to show you a lot of things about how covalent bonds actually work by drawing these structures. Now the dot diagram thing we've already done, but let's just practice it quickly. Okay? If I'm going to draw the dot diagram for carbon, how many dots do I put around carbon? Okay, I heard 6 first, and then I heard 4. Why not 6? That's the total number of electrons, right? But we're not worried about the total, we're worried about the valence electrons. Okay, so the valence electrons, there's only 4, and how do we know that there's 4 valence electrons? That's the group number, okay? Well, yeah, minus 10 or take away the first number, okay? So 4 on carbon. Again, I still don't care exactly where you put these. You can pair them up if you want. You can put them all around, whatever. Okay, so that's carbon's electron dot structure, or the dot diagram. So then nitrogen, I don't know that I need to do all of these, but nitrogen is going to have 5, okay, 5 valence electrons. So you put 5 dots around it. Oxygen would have 6, iodine would have 7, and magnesium would have 2. Everybody okay with that? No? Didn't catch that? All right. Nitrogen, again, do you look at where nitrogen is on the periodic table? It's all based on where they are, okay? This is number 7, right? That means it has 7 total electrons. But that doesn't tell you how many valence electrons it has, okay? Valence electrons, you count groups. So this is group 15 right here. Group 15. If you count all the way across, this is number 15, okay? So you just take off that 1. Remember, the 1 doesn't count. You look at the last number in the group number, and that'll tell you the number of valence electrons, all right? So because this is group 15, 5 valence electrons. Group 16, 6 valence electrons for oxygen. And then iodine, group 17, there are 7 valence electrons. Yes, sir? Yeah, we're just reviewing it. And then we're going to go into stuff that's more complicated. All right, but does everybody remember how to find valence electrons? Everybody okay with drawing your dots? All right. What's happening? Everything was flashing. Okay. So, okay, you got the practice right there. So you can write those down if you want to for carbon, nitrogen, oxygen, iodine, and magnesium. Valence electrons in a covalent bond, they're distributed or shared, okay? I'm sorry, they're distributed as shared or unshared electrons, okay? And if they're shared between 2 atoms, then we call them bond pairs, And if they're not shared, then we call them lone pairs. All right? So when two atoms come together and they form a bond, a covalent bond, they will share some of their electrons, and then they'll hold on to some of them just kind of on their own. All right? So an example of this is HCl. So you can see the picture here, right? Now, poor hydrogen doesn't have any unshared electrons because it only has one electron total, right? So it has to share that one with something else in order to form a bond. But hydrogen's okay with that because now it's kind of like it has two in the middle here, and so it's going to be like helium, okay? So remember, every atom, their strategy is to be like a noble gas, all right? So if you've got a hydrogen, and this hydrogen has one electron, and then you've got a chlorine, and that chlorine has 1, 2, 3, 4, 5, 6, 7, okay? Then one way that they can both kind of be happy here, because the chlorine wants an electron, and really the hydrogen kind of does too, because the hydrogen wants to be like helium, right? And the chlorine wants to be like argon. So if those two pair up, they can share these two electrons in between them, like this. Does that make sense?
Oh, yeah.
And then these two electrons right here, that kind of forms a bond between them, because they're both holding on to those two electrons as though they belong to the hydrogen. You know, the hydrogen's holding on to those two as though it belongs to the hydrogen. And then the chlorine's holding on to those two electrons as well. So they're bonded. All right? Now, a lot of times to show that bond, instead of putting the two electrons in the middle, we draw a line. It means exactly the same thing. Okay? Everybody understand that? So instead of drawing the two electrons there, there's this line. And this line really just means there's two electrons here being shared. Okay? And that's the bond. Now, what if I draw two lines? Can I do that? Okay, that would be 4 electrons being shared. Each line represents 2 electrons. Now, you can't do that with this particular molecule, but there's some where that works. Okay, so each line that you see, you should be thinking 2 electrons when you see that line. All right? And this is called the Lewis structure, which, again, we've already kind of done this, okay, but now we're doing it for covalent compounds. All right. In case you're interested, we're not going to talk much about this, but you remember how we talked about orbitals? Electrons exist in orbitals. You remember the hotel diagram and everything? Okay? So when you draw those orbitals for something, they kind of look like this, all right? So the chlorine, this is a p orbital. You remember the p orbitals kind of look like dumbbell shapes? And there's 3 different directions that the p orbitals can point, and the other one would be coming out of the screen and going back into it, right? So those are your p orbitals, and then the hydrogen just has an s orbital where its 1 electron is. Well, this hydrogen's s orbital and a chlorine's p orbital overlap, and now they're sharing these 2 electrons, because remember, these up and down arrows represent electrons. Okay? So that's kind of what's actually happening when a bond forms, is those orbitals are moving next to each other and kind of overlapping. All right? There's more to the story than that, but that's about as in-depth as we're going to get with it this year. Okay? Oh, hey, there's an arrow where I circled. All right, so now we're going to practice actually building these electron dot structures, okay? And the example we're going to use here, the example you have on letter G is NH3, okay? NH3, it would be worthwhile to know that the name for that is ammonia. What have you seen that's kind of close to the name for that? Ammonium. Do you remember where ammonium was? It was not on the periodic table. It was on your polyatomic ion chart, okay? So ammonium is actually NH4+. You can see that looks very similar to this, right? This is ammonia. So that might be a good one to remember. Hint, hint. Because it might be on a test or a quiz, all right? So ammonia NH3, all right? So first thing that we have to do, if we're building a dot structure for these things, is we need to decide on a central atom. Okay, and now here's where we learn the process of doing this. And it's a fairly straightforward process. I think you guys are going to be fine with it. But there are 4 atoms here. So which one do I put in the middle? there's 4 atoms. There's 1 nitrogen and 3 hydrogens, right? So there's 4 total atoms that we have to put in our Lewis structure here. Which one do you think might go in the middle? Ammonia is the whole thing, right? Okay, so our 2 choices are nitrogen or hydrogen, right? Now there's a couple of reasons that I probably would put nitrogen in the middle. Here's why. Number 1, which one of these has more electrons to share? Well, either nitrogen or hydrogen, right? Okay, how many electrons does hydrogen have total? 1. That's not very many electrons to share, right? How many valence electrons does nitrogen have? 5. So nitrogen has more electrons to share in the first place, okay? Now the other reason that I might put nitrogen in the middle is because there's only 1 nitrogen, right? And there's 3 hydrogens, so the hydrogens can go around the nitrogen. Does that kind of make sense? All right, so we put the nitrogen in the middle, put the hydrogens around it, okay? So that's the first thing. That makes sense? Okay, all right. So the step number 1 here underneath G says decide on the central atom. The rule is it's never hydrogen. Hydrogen never goes in the middle. Any ideas why hydrogen might never, ever, ever go in the middle? Well, it only has 1 valence electron. How many does it want?
4.
Okay, remember, hydrogen is one of those weird exceptions that doesn't need 8, right? How many does it want? It wants to be like helium, right? Helium only has 2 electrons, so hydrogen doesn't need 8 around it. If you put it in the middle, it's going to have too many electrons around it, okay? So we don't ever put hydrogen in the middle. Just remember that, okay? So nitrogen goes in the middle, and I don't care how you do this necessarily, but just put the 3 hydrogens somewhere around that nitrogen. If you don't like that because it's not symmetrical, fine. I know something you don't know here, so that's why I'm doing it this way, okay? Every time I say I know something you don't know, it makes me think of Princess Bride. And probably none of you guys know that movie, do you? Some of you do? Okay. I am not left-handed. I know something you don't know. All right. So anyway, some of you get that joke, most of you don't. All right. You ready? Step number 2. Well, first, what we're going to do here, and this is not really the way these bonds occur, but it's just the easiest way to do it. We take all the valence electrons we have available, and we kind of just put them all together for a minute. And then we figure out how to spread them out around the entire thing, okay? So we need to count up the total number of valence electrons that we're dealing with here, all right? You already told me how many valence electrons nitrogen has. It has 5, right? Everybody there? How many does hydrogen have? 1. There's 3 of them, okay? So what's the total number of valence electrons here? We've got 8 total valence electrons that we're working with. 1 from each of the hydrogens, that's 3, plus the 5 from nitrogen, that's 8. Okay? Everybody with me? You confused about the 8 part? Okay, so we've got I'll just draw the Lewis structure for all of these right now. 1, 2, 3, 4, 5 for that one, right? And we've got 3 hydrogens. So I'm just counting up the total number of valence electrons that we have, okay? All right, so we've got 8 to work with. Now we've got to spread those out in a certain way, and the rule here is we want everything to be like a noble gas. That's the goal. So hydrogen needs 2 electrons. Everything else pretty much needs 8, right? Yes, ma'am. Oh, were you going to suggest like how to do it? Okay, hang on just 1 second. So we've got 8 electrons, which is 4 pairs. We want to keep pairs together. That just works out better for us, okay? Number 3, form a single bond between the central atom and each surrounding atom. Okay, we know for NH3 to form, there has to be a bond here and here and here. So we need at least 2 electrons in each of these places, right? So I'm going to put 2 here, 2 here, and 2 here. I just used up 6 of my 8 electrons, right? So now I have 2 left. We just did step 3, actually. form a single bond between the central atom and each surrounding atom, okay? Step 2 was the 8 part, where we figured out how many total valence electrons we had. Okay? Now, what do we do with the last 2 electrons that we have left over? Put on top of the... Okay, because the nitrogen only has 6 electrons around it right now. It's not quite happy, right? So let's put 2 electrons right here as an unshared pair or a lone pair. Does everything look good now? Okay, so this hydrogen's happy because it has 2. This hydrogen has 2. This hydrogen has 2. And the nitrogen has 8. So now if you want to, now you're not necessarily required to do this. I don't think this is a step on here. No, it's not. But if you don't like writing it that way, then you could also write it like this. You could make a line in between the nitrogen and the hydrogens, and then just put your extra electrons up on top. Either one of these is an acceptable way of writing the Lewis structure. Okay, you guys with me? It's a little bit complicated. The more you practice this, the more it'll make sense. Okay. So that's how it works. So then the step 5 and step 6, it says check to make sure there are 8 electrons around each atom except hydrogen. Hydrogen should only have 2. So we already did that, right? That's step 5. And then step 6, also check the number of electrons in your drawing with the number of electrons from step 2. It's always good to just check and make sure you didn't put in extra electrons somewhere on accident. We have 2, 4, 6, 8 electrons in our drawing. That's how many we started with, right? That's how many we said that we had to work with. So that's good, okay? If we had put in 10 down here, then you'd have to go back and do it over again because you only have 8 electrons to work with. All right? Okay, so let's do a couple examples here. You've got H2O. Let's do H2O and CH4, okay? See if we can figure those out. I'm not sure. I don't know why I'm erasing this if we've got slides for this. Keep going, keep going. Keep going. Okay, so now we're going to draw water. So let's just work our way through our steps. Go back to step number 1. Decide on the central atom. Why oxygen? Because it's never hydrogen, right? Okay. There's some other rules that I'll have to teach you as we go along for strategies for finding the central atom because hydrogen's not in every single one of these. But oxygen's going to go in the middle, so I'll just put hydrogen, one hydrogen on one side, another one on the other side because we have 2 hydrogens in this compound, right? Second step, how many valence electrons are we working with here? How many does oxygen have? 6. How many does each hydrogen have? 1. And there are 2 of them. So 6 plus 1 gives us 8. We're working with 8 again. Not always 8. Okay? So I've got everybody okay with that. I've got 8 total electrons here. Okay. So then step number 3, form a single bond between the central atom and each surrounding atom by putting 2 electrons there. Okay, so we've got to put 2 electrons here, 2 electrons here. Why it's 8? Because oxygen has 6 valence electrons. You see that? Hydrogen has 1, and there's 2 of them. Okay? And again, I mean, if that's confusing you, then just draw it out for the first few times, right? Okay, here's oxygen, here's hydrogen, and then just count dots. Okay? All right, so you've got, we've used up 4 of the electrons out of our 8, right? We've got 4 left. Where am I going to put the last 4? Okay, top of the O, bottom of the O, right? That's step 4. Remaining electrons form lone pairs to complete the octet. And we don't want to put lone pairs around the hydrogen because the hydrogen's okay with just 2 electrons. So we don't need to put any more around hydrogen. Every year this happens. I get on a test or a quiz, I get a student who starts putting all kinds of electrons around hydrogen. Okay? And then that makes me really upset when I'm grading their paper. And sometimes I just take it and rip it and throw it in the trash. No, I'm just joking. That doesn't happen. But, you know, I think about doing that. So don't make me think about ripping up your paper and throwing it in the trash, okay? Just 2 electrons on hydrogen only. Everybody got that? 2 electrons on hydrogen. That's it. Okay. So this is our Lewis structure for H2O. Everybody all right with that? And then, again, 5 and 6 are kind of just checking steps. Make sure there are 8 electrons around each atom except for hydrogen. Oxygen's good. It's got 8 around it. And then make sure that you didn't use more electrons than you were supposed to here. Okay? We started with 8. We used 8. So we're good. All right. Why don't you try CH4 on your own? See if you can do that one, and we'll talk about it in a second. Yeah, the one after CH4 we're going to have to talk about. Yeah, there's something special you have to do for that one. So, okay, so try CH4 real quick. I'll give you a minute or two, and then we'll talk about it. And I'll pause the video so you guys aren't bored on the video. All right, so very quickly on the CH4. Central atom? Carbon. Since there are, 4 sides here, I'll put one around each of the 4 sides. Total number of total number of valence electrons that I'm working with here. 8 again. I promise it's not always 8. Okay. So then I take those 8 valence electrons and I'm going to first use them to make bonds, right? 2 here, 2 here, 2 here, and 2 here. Oh. Well, I guess we're done, aren't we? Okay, because we just used up 8, so there are none left. Is everything happy? Yeah, everything's good. Carbon's got 8 around it. Each of the hydrogens have 2. Another way to draw this, and I didn't mention this on the last one, but this is just as good as that. Okay? Yes. I think I was going to say no if you didn't put that emphatic please on there at the end. All right. CO2. Here's where it gets a little tricky, okay? And this is not one of the rules. I wish that it was. You might write this in somewhere, but let's do it first, and then I'll have you write it in, okay? So, CO2. What's the central atom here? Ooh. Well, okay. Here's the thing. Symmetry is kind of your friend on these. All right? So if I put an O in the middle, that means I've got a carbon on one side and an O on the other side. Ook. I don't really like that, okay? So what if we put the C in the middle? Then it's a little more symmetrical, right? All right? Now that doesn't always work. Let me tell you a good rule here, all right? When we're not dealing with hydrogen, you ready? This is a good rule. Almost always, the one that's listed first goes in the middle. Almost always. Okay? You want another good rule? The one that's the least electronegative goes in the middle. Now that'll work every time. You remember talking about electronegativity? You got that chart? Remember with, oh well, yeah, you weren't here. But you got that chart with all the values on it? You guys remember that? Fluorine's the most electronegative on the periodic table. You guys have a periodic table that has numbers on it. You figured out the difference in electronegativities, and that would tell you whether it's covalent or ionic, right? Okay? So if you have that chart out, you can always figure out which one goes in the middle because it's the one with the lowest number. All right? So guess which one never, ever, ever goes in the middle besides hydrogen? We talked about hydrogen already. Fluorine never goes in the middle because it's the most electronegative on the periodic table. So you don't put fluorine in.
So whichever one has the least electronegativity always goes.
Right. And just the convention for writing a formula, the one with the lowest electronegativity is always written first in the formula. So that's why it works to look at the one that's first in the formula.
So that
Okay. This works almost every time. Yeah. When you're not dealing with hydrogen, it pretty much works.
that's the place where a lot of type of stuff.
Mm-hmm. Yeah, I'll let you have the electronegativity chart on the quiz so that you know which one goes in the middle.
I get that, John.
Yes. Okay, so we figured out which one goes in the middle. That's a good first step, all right? Second step is counting how many valence electrons we're dealing with.
Whoa, hold on. Well, there's 15 since there's 6 regularly in oxygen, we just have to get
Okay, so there's 6 in each oxygen, right? So that's a total of 12, plus the 4 from carbon. Everybody all right with that? So we got 16 electrons that we're working with here.
Wait, say that again.
Well, and again, just draw them out, right? 1, 2, 3, 4, 2 oxygens. Each of them has 6. So just total up your electrons here, and it's going to be 16. Okay? 2 in the middle of each of the bonds, right? That leaves us with 12. Okay? Now, what you want to do now, and we haven't had this situation yet, but now we're in a situation where everything wants 8 electrons, right? There is no hydrogen here. Okay, so here's the thing. The strategy you want to use is start on the outside and work your way in. I would write that down if I were you, okay? On this kind of molecule, you want to start on the outside, work your way into the middle. Now, there's a reason for that. Remember I said the ones that are more electronegative are on the outside? So guess which ones grab the electrons first? The ones that are on the outside, the ones that are more electronegative, because they're like, no, give me those electrons, I'll take those, okay? The one in the middle is the one that doesn't have as much grabbing power, okay? All right, so what I'm going to do is I'm going to make sure the outside atoms are happy first. I need to put 1, 2, 3, 4, 5, 6 around this oxygen. Now it's happy. 1, 2, 3, 4, 5, 6 around this oxygen. Now it's happy. But we got a problem. How many electrons do I have left now? None. I just used all 12 of them, didn't I? Okay, so here's the trick. If you run into this situation where you ran out of electrons and not everything's happy yet, the carbon is going to say to the 2 oxygens here, well, this doesn't work. I'm not happy. I don't have 8 valence electrons around me right now, okay? So the carbon and oxygen work out a deal where they're going to share 2 pairs of electrons in the middle, okay? So I'm going to take one of these pairs, and I'm going to put it in here, okay? Why would I put it there? Because now they're sharing 2 pairs in between them. So now it's like each of them, so now the carbon's up to 6, right? It only had 4 before. Put on the top of the carbon, because then the oxygen doesn't have them anymore, right? So here the oxygen still has 8 because it's sharing the 4 in the middle. Okay, now I'm close with the carbon, but I'm not quite there. Any ideas what I need to do now? Let's do the same thing on the other side, right? So we put these 2 in the middle, and then it becomes this.
Why isn't there 2 dots on the top of the carbon and the bottom? Okay, dot on top of the carbon. Because the oxygen.
Because then the oxygen wouldn't be happy, right? If I took the dots and put them on top and bottom of the carbon, now it's not being shared with the oxygen anymore, so then all of a sudden the oxygen doesn't have 8.
But isn't there 4?
Yeah, so count now we need to do our step where we count the total number around each particular atom. So look at this oxygen on the left first, okay? It has 2, 4, 6, 8 around it because we count the 2 in the middle as being part of the oxygen, okay? This carbon has 2, 4, 6, 8 around it, so it's happy, okay? This oxygen has 2, 4, 6, 8 around it, so it's happy. All right? Now, what we call this right here, this is called a double bond. Yes?
And like, but you need to get 18 electrons, then 2 bottom ones go over to the carbon and share that.
If you had 8, yeah, and we're going to get to some situations like that. Yeah. Okay, so the other way that you can draw this, and I showed this to you earlier, 2 lines, right? By the way, you know what this molecule is? Well, I guess it says it up there. I forgot that it said it up here. Carbon dioxide, right? So here's the structure. This is what carbon dioxide, that stuff that you're breathing out all the time, that's what it kind of looks like. That's not really what it looks like, but that's the Lewis structure for it, all right? Everybody okay with that? That one's a little tricky because we had to do a double bond thing there. Now I'm debating, do I teach you resonance today or do I wait? Yeah, I think we'll stop there for now. Now what I do want to do is give you a practice worksheet. That's the wrong one. Oh, you know what? We haven't done the polyatomic ions yet either. Okay, so here's what we're going to do. We'll take it nice and slow with this as far as the quiz is concerned. This worksheet that I'm giving you, you only need to do the group A on this worksheet, okay? There we go. So again, let me say this to make sure everyone heard me. You are only doing group A on this one. Oh, no, wait. I changed my mind. You can do, this is, sorry to do this out of order, but you can do group A, and you should be able to do group C also. Group C. Okay, now let's talk a little bit about group C, because those are the ones that might give you a little bit of trouble. And I think I need to give you one more of those. Okay, so let me go ahead and open this up on here, and then so that you can see this on the video as well. Where are we? Yes. The big one. Oh, it's turned sideways, of course. Okay. Listen up. This is important because these are the kinds of things you're going to see on your quiz tomorrow. All right? So with these first ones up here, I think you're going to be fine. I don't think you're going to have too much trouble with those. Those are nice, simple ones like the ones that we talked about. Down here on the multiple bonds, group C, these are the other ones that you are responsible for tomorrow. We've already done CO2, right? Yes. So there's one like that. Now, there's a couple of these that have more than just two elements in them. All right? But the rules don't change here. Okay, so let's look at HCN, for example. That's a good one to do. Okay, so which one goes in the middle between H, C, and N? Well, which one, let me ask you this, which one for sure doesn't go in the middle? Why not H? Because H never goes in the middle, right? Okay, so it's between carbon and nitrogen. So carbon's the next one listed. So that's probably the least electronegative. If you want to look on your chart, you can, just to make sure. Carbon is less electronegative than nitrogen. It has a lower number. So carbon goes in the middle, all right? So we'll put carbon in the middle. We'll put nitrogen on one side. We'll put hydrogen on the other side. This one, unfortunately, can't be symmetrical because we have three different elements here, okay? How many valence electrons are we working with? Okay, are we in agreement on 10? Okay, so 10 electrons. There's 5 from the nitrogen, 4 from the carbon, 1 from the hydrogen. You add those together, you get 10. We need to use 1, 2, 3, 4 to make our bonds here, right? So now I've got 6 left. Now again, the rule is, first thing you're going to do is take care of the ones on the outside, right? Hydrogen's happy. Hydrogen only needs 2, so don't worry about hydrogen. Nitrogen, 1, 2, 3, 4, 5, 6. We have now used up all of our electrons. But you knew that was going to happen because group C is multiple bonds, so you're going to have to form double bonds in that group. Okay? So now what? No, we're not done. Carbon's not happy, right? Carbon only has 4 around it. Okay, but I have to do it twice, don't I? Can we do that? Can we do a triple bond? Okay, so maybe that pair and this pair go in the middle, and so we end up with something that, I'm writing it up here, something that looks like this. Okay? That was probably a bad way to write that just now. But yeah, that's your HCN. Now, oh, thank you. And then there's 2 right here on the side of the nitrogen, right? Because we still have those 2 left over that didn't go in the middle. So 2, 4, 6, 8, 10. Everything's happy because the carbon has 8 electrons around it. The nitrogen has 8 electrons around it. And you can write this. The other way you can write this is like this, okay? So the answer is yes, triple bonds are possible. That's as far as they go. There's no such thing as a quadruple bond, okay? You shove, 6 electrons in here, and that's as many as want to be in one place at one time, okay? Why carbon would have to have 6? No, carbon needs to have 8. Yeah. There's two on this side, and then 6 on the other side, so, yeah. All right, so that's basically how that works with the multiple bonds. We'll practice some of the other stuff tomorrow, okay? Turn this off.